I will make you understand.
I'll now invite Lord Monckton to make his opening remarks. Lord Monckton, please.
My lords, that's me. Ladies and gentlemen, the climate, like the cricket, is chaotic. Who would have believed that England would not only win back the Ashes, but would then hang on to them the next time round? Just thought I'd rub it in. Now, because the climate is chaotic, or even if it isn't, it acts as though it were, it is not predictable in the long term. And that, if you do science by consensus, and that was the central argument that Professor Dennis offered us today, that there is a consensus, if you do climate by consensus, then the consensus is expressed in the documents of IPCC, the Inter-Governmental Panel on Climate Change. And they say that the climate is a coupled, non-linear, chaotic object, and that therefore the long-term prediction of future climate states is not possible.
This is a very strange statement, as the IPCC has included projections about what our future climate might look like in every single report they published. They even give different types of outcomes depending on the amount of greenhouse gases we emit. What he actually seems to be quoting from the 2001 IPCC report. One of the places this is mentioned is in the section 14.2.2.2, balancing the need for final scales and the need for assemblies, the Working Group 1 report, and it says the following. In climate research and modeling, we should recognize that we are dealing with a coupled, nonlinear, chaotic system, and therefore that the long-term prediction of future climate states is not possible. The most we can expect to achieve is the prediction of the probability distribution of the system's future possible states by the generation of assemblies of model solutions. If you read the entire section, you will find that they mention computational restrictions as one of the reasons that limits them in the amount of detail they can include in the models. And let's not forget all the other factors that make it hard to project what happens. For example, how much CO2 we emit, as this hinges on economic, social and technological developments. Because of reasons like these, it is not possible to give the one most likely scenario for how events will play out, its consequences and what the eventual future climate will be. But it doesn't mean that you can't predict what might happen given a certain scenario. The IPCC explains this in, for example, section 1.2.2, Natural Variability of Climate, of the Working Group 1 report. Many processes and interactions in the climate system are nonlinear. That means that there is no simple proportional relation between cause and effect. A complex, nonlinear system may display what is technically called chaotic behavior. This means that the behavior of the system is critically dependent on very small changes of the initial conditions. This does not imply, however, that the behavior of a nonlinear chaotic system is entirely unpredictable, contrary to what is meant by chaotic in colloquial language. It has, however, consequences for the nature of its variability and the predictability of its variations. The daily weather is a good example. The evolution of weather systems responsible for the daily weather is governed by such nonlinear chaotic dynamics. This does not preclude successful weather prediction. In other words, what they say here, and throughout the entire report, is that complex systems like the climate can be predicted. We just have to be aware of where the limitations are and how we should deal with them, which is a far cry from saying that our future climate cannot be predicted. An illustration of what I mean with these uncertainties, one of them being climate noise, is given by Ben Center, one of the IPCC authors.
This is from a climate model, a Japanese climate model. These are from experiments that were performed in support of the IPCC's fourth assessment report in 2007. What you see here are tropospheric temperature time series, and you can see that there's this black line here is this small overall warming trend. This is an experiment where a model is driven by changes in greenhouse gases, changes in the sun's energy output, changes in aerosols, ozone. We call them also colloquially everything and the kitchen sink experiments, where you try and drive a climate model with your best estimate of the actual factors that have been important over the 20th century. And you can calculate from this climate model something akin to the satellite temperatures that I've showed you. And in this particular run of this Japanese model, you have a La Nina, that's that blue thing, near the end, which tends to cool it down. And you have an El Nino near the beginning, that's the red thing, which tends to warm things up. Because this is a short record, only a little over 20 years, and you have a warm blip near the beginning and a cool blip near the end, you don't get much overall change. Now, when you run the same model, but starting from a different initial state, back, say, in 1850 or so, you get some different sequence of El Niños and La Niñas. These are free-running models, if you will. They generate their own climate noise. And if you start from different initial conditions, very soon you get a different sequence of El Niños and La Niñas. You see that very clearly here. This is, again, the same model, the same human-caused forcing factors that it's being run with, but it has a different sequence of El Niños. In this case, it has an El Niño near the end of the series and a La Nina near the beginning, so it shows a larger overall warming trend, because it has a cool blip near the beginning and a warm blip near the end. And you can see the same thing here. This is the same model, just different realizations. And each one of them has a slightly different sequence of wiggles, ups and downs, different overall trends. This is the effect of noise. This is climate noise. Obviously, in the real world, we don't have the luxury of rerunning the real world many times. We only have one sequence of climate noise and one sequence of how the real world has responded to human-caused changes in greenhouse gases. But in the climate model world, you can essentially sort of rerun the 20th century many times and get many different sequences of these things. And what you do then at the end is you average over all of these things. You average over these 5 realizations, and that beats down the noise, because the noise is not correlated from one realization to the next. So you get a better estimate of the thing you're really interested in, which is the slow overall increase in temperature, in this case in response to human-caused changes in greenhouse gases and all that other nice stuff.
So the IPCC report doesn't say they can't predict future climate states, as they can and do give predictions for likely future climate states. Also, I find it odd he's giving a direct quote from the IPCC 2001 report, when the report published in 2007 is the most recent one, which also gives a similar statement about our chaotic climate system and what this means for predictions, albeit updated with the latest research.
The Royal Society, in a complete rewrite of its original disastrously unscientific statement about the climate, now says we do not know how much the planet will warm as a result of our activities.
Monckton is most likely referring to the document Climate Change Guide that was released by the Royal Society in September 2010, and several other contrarians and so-called skeptics have made similar claims about it. This claim has its probable genesis from sentences like the one in the second paragraph of the introduction, where they state the following. The size of future temperature increases and other aspects of climate change, especially at the regional scale, are still subject to uncertainty. They expand on this in paragraph 40 in the section Future Climate Change, and it states, as with almost any attempts to forecast future conditions, projections of future climate change depend on a number of factors. Future emissions due to human activity will depend on social, technological, and population changes which cannot be known with confidence. The underlying uncertainties in climate science and the inability to predict precisely the size of future natural climate forcing mechanisms mean that projections must be made which take into account a range of uncertainties across these different areas. The 2007 assessment by the Inter-Governmental Panel on Climate Change, IPCC, made projections of future changes using a number of possible scenarios of future emissions, based on a diverse range of assumptions. The IPCC's best estimate was that globally average surface temperatures would be between 2.5 to 4.7 Celsius higher by 2100 compared to pre-industrial levels. The full range of projected temperature increases by 2100 was found to be 1.8 to 7.1 Celsius based on the various scenarios and uncertainties in climate sensitivity. So they actually do give a most likely increase in temperature in the document they released. And their statements reflect what has been written in the IPCC documents.